My great ambition was to fly.
The curved blades of the turbine change the kinetic energy into turning power. In this engine, the turbine is designed to take the greatest possible amount of energy from the gas stream.
Good afternoon, Engineer Bernardes. Good afternoon, classmates. Today, we are going to discuss the design of gas turbine blades. But first, let us recall what gas turbines are. Gas turbines specifically are machines composed of alternating stationary and rotating airfoil section blades. The turbine blades catch the rapid airflow and rotate to drive a spinning shaft that turns the fan and compressor at the front of the engine. The turbine essentially powers the rest of the engine, harnessing energy from the combustion chamber to maintain steady air intake and compression. Air passing through the turbine loses energy to the rotating blades, but what remains moves into the final exhaust stage of the engine where it is expelled to produce thrust. Turbines may also be classified based on whether the gas flow direction within its passage is axial, radial, or mixed.
Moving on, we have the three types of turbines, namely axial, radial, and lastly, the mixed turbine. For axial turbines, this is a turbine in which the flow of the working fluid is parallel to the shaft. It has a similar construction as an axial compressor, but it operates in the reverse, converting flow of the fluid into rotating mechanical energy. Next we have is radial. This is a turbine in which the flow of the working fluid is radial to the shaft. Lastly, we have the mixed turbine. Now, in a mixed flow turbine, the inlet flow is at an angle between the complete radial and the axial design. Since it is a cross design of both axial and radial, it then has the characteristics of both the kind of turbines mentioned.
How turbines start. Through activating the APU, electrical power of the aircraft will be turned on at the same time powering the AEC. The AEC then takes over the entire engine to start its operation, sending pneumatic pressure from the APU to the accessory gearbox which rotates the N2 shaft. As N2 rises, airflow will be established in the system causing the engine to enter standby mode since the intake fan and compressor is connected to a single shaft along with the turbine which passively supply a percentage of its power to the fan and compressor.
Next, let's move on and talk about what is a turbine blade. A turbine blade is the individual component which makes up the turbine section of a gas turbine or steam turbine. The blades are responsible for extracting the energy from the high temperature, high pressure gas produced by the combustor. The turbine blades are often the limiting component of gas turbine, in which to survive in this difficult environment, turbine blades are often used in exotic materials such as superalloys and many different methods of cooling that can be categorized as internal and external cooling, as well as the use of thermal barrier coatings. To properly introduce turbine blade, let's watch a video about the birth of turbine blades.
We're here in the workshops of Saint-Quentin-en-Yvelines, where Damien is busy assembling a LEAP engine turbine. He has worked for years here in the assembly department, so he's perfectly familiar with every part of every turbine. He could practically assemble them with his eyes closed. The part that Damien is assembling here are stage 2 nozzles for the LEAP engine. And Damien will tell you how this part was made. What? You don't know? Really? Where does this part come from? It says Gennevilliers. All right then, let's go and see. Here on the Gennevilliers site, many different parts are made for civil and military engines. And it all starts here in the design office, where the team designs parts according to strict specifications. While incorporating thermal and aerodynamic constraints, as well as mechanical requirements, the team precisely models the part. We can see our turbine blade, which for the moment exists in a virtual state. To make it into a real object, the CAD file is sent to the Tools and Product Method office, where they'll work on it to adapt it to production. The office works collaboratively with the Process and Product Method team. The goal is to jointly define how to produce this turbine blade industrially. First, the team models a cluster structure specific to industrialization. Then it develops injection tools, in other words, molds. The production of these molds is outsourced, but of course, they are all systematically checked by the office. So far, so good? Let's move on to production. To obtain these parts with complex shapes that include voids, the team uses a 6,000-year-old method, lost wax casting. You start by producing an object in the shape of the desired cavity, the core. Here we inject a mixture of binder and ceramic into this machine to produce that famous core. This material is still fragile. We therefore need to cook the core in order to harden it. This operation is carried out in baking sand. This enables the core to keep its shape even under heat capable of deforming it. Our core is now much stronger. All the cores are meticulously deburred and checked. Once prepared, they are placed in the famous injection mold. The 4 cores inserted here will form the 4 cavities of our turbine blade. Wax is injected. And what do we discover when they come out? Wait for it. Magnificent. This is our turbine blade, made of wax. It immediately undergoes ultrasound and radiography tests to verify that the core is correctly centered in the wax and that it didn't crack during the injection. The wax model is prepared to form the famous cluster developed by the method office. These clusters are taken for cleaning, which is essential to remove all traces of handling or release agent. Because the blades must be perfectly clean so that nothing interferes with the adherence of the material, they will be covered in the ceramic slip. Slip is a kind of liquid paste. The clusters are soaked in it, then sprinkled with ceramic sand. Once dried, the whole forms a crust. This operation is repeated several times until a sufficiently thick ceramic shell is obtained. Now we have to melt the wax that's inside. It's a delicate operation because the clusters are composed of wax parts encased in ceramics. The wax will expand in the heat, but not the ceramics. So to prevent the ceramics from cracking, the operation is carried out under pressure in an autoclave. Then a cooking operation hardens the shell and burns all the wax residue. The ceramic core is maintained inside. Now we need to check the impermeability of the shell in which the metal is going to be cast with a non-destructive process, of course. So another radiography or ultrasound test? No? Really? With methyl blue solution, of course. The shell is filled with it, and the color will reveal the slightest defects by making them turn blue, like that little bit here, and right there. The compliant shells are then taken to be cast. Not quite yet, actually. So what do we have in here? Some references require preparatory wrapping, because when the metal is cast, upon reaching the edges, it starts to cool down, so to harden, and that can prevent an even distribution in the finest parts. Pre-wrapping ensures that the temperature is controlled for specific parts. So all good to go this time? The shells are ready, so we start to preheat. The metal is loaded and brought to the melting point. The preheated shell is put in position. Casting completed. The cooling stage is crucial. It's the precise control of the cooling process that gives the material its high-performance thermomechanical qualities. A cooling ring is used to control this phase of directed solidification. The metal retracts slightly, which causes the ceramic layer to develop cracks. It almost makes you want to shake it off to completely clear the part. In fact, that's exactly what happens during the shake-off operation. Here, finally the rough blade is revealed, still arranged in clusters. Now we separate them. You will notice that our core is still inside. To get rid of it, we're going to dissolve it in a soda bath. That's the machine just behind. The turbine blades are taken for soaking, and when they come back, how do they look? Perfect. There is still one finishing step left to get this blade spick and span. But in fact, is this part compliant? It undergoes a full range of tests: macro control to inspect the grains, dye penetrant testing to identify visible surface defects, ultrasonic thickness control, dimensional inspection, and internal health control by digital radiography. What about traceability? Time to head over to the machining assembly and coating unit. Metal stellites are added to the parts that will be in friction to reduce wear and tear. A grinding operation called rectification will give the part a clearer and more precise shape. An adjustment will round off sharp edges. These finishes are very precise. This three-dimensional measuring machine performs an impressive 150 measurements per part. According to their position and their function in the engine, some parts will be subjected to very high temperatures. In order to cool these parts, a drilling operation adds holes to accelerate the circulation of air. This micro-drilling is done with water. Using an electrode all the same, calibrated to the diameter of the hole is hollow so that water can pass through. Seeing how fine the rod is, you immediately understand that the drilling action is not mechanical, but electric. Some parts are now going to be covered with several small complementary parts. These complementary parts are attached using a solder bead and then melted in the oven. The furnaces are also dedicated to heat treatments or thermochemical treatments, where the parts are finished off with an external coating. Here, finally, is our finished turbine blade. An airflow test, as well as penetrant and radiography tests, check the quality of the part. But before it goes off for delivery, this machine still performs some operations. Laser marking, adding a manufacturer's number, weighing, and in the final touch, the turbine blade's position in the box is photographed to ensure complete traceability. Now we're all done. The box is ready. All we have to do now is deliver it to Damien, our fitter in Saint-Quentin-en-Yvelines. Keep up the good work, Damien.
Next is design optimization. The blades are divided into 4 parts. The first part will be the airfoil, a cross-sectional shape of an object whose motion through a gas is capable of generating significant lift. The second one, the platform, a piece of metal located in a cavity underneath 2 adjacent blade platforms. Platform does not contribute significantly to blade structural behavior. The third one, shank. The shank includes a downstream cover plate and a downstream angle wing that extends axially from the downstream cover plate. Shank sustains a major stress flow from the dovetail to the airfoil due to the rotation. The fourth one, dovetail. Type of blade attachments used to connect blades to a disc in a fan and compressor. A blade is inserted in a slot of a disc mounted on a rotating shaft. When the turbine is operating, air pressure is applied to the surface of the airfoil, and an inertia body force is applied to the whole blade structure due to the rotation. The inertia body force contributes significantly to the blade structural deformation. To simplify the problem, fluid pressure is neglected in the finite element and sensitivity analysis. The profile of the airfoil is determined from aerodynamics consideration and is not considered for shape design changes. However, the shape of the shank and the position of the dovetail can be modified to improve structural behavior of the blade. Here's some additional information about the innovation in blade design that optimizes its efficiency.
Today's energy mix combines endless power of nature with highly efficient power plants, transmitting energy with human engineering. We challenge technology every day, and sometimes it's the small things that make the difference.
If you look at this small little turbine blade, it actually looks very tiny and very simple. But at the end of the day, it is one of the most challenging applications, I guess, out there for metal additive manufacturing. Not only did we simply 3D print an existing design of that blade and test it, but we also changed the design of the blade itself in order to improve the performance of the part.
Together with EOS, we are working with the productivity improvement, with the, let's say, going down with the manufacturing cost, and I believe that we really can add value to both of us, and by doing this, support the rest of the industry.
It's easy to generate a prototype or a sample, but it's very hard to achieve a physical part that actually stems from digital data with a defined process chain behind and ends up in a rig test and withstands the requirements for a gas turbine component. And this is something that we managed in this project.
So now, with this technology, we really can speed up quickly, but what needs to be done? We need to change the mindset in our designers, so they need to understand this flexibility.
1250 degrees, 1000 miles per hour, 11 tons weight pulling at each blade. If you can print a turbine blade, you can print pretty much everything. It is designed with Siemens NX, produced on AOS equipment, powered by Siemens automation technology.
Today's blade design is based on numerical methods and optimization, and is often used to improve the profile performance. These profiles do not follow a standard like the NACA profiles. The gas turbine technology is at such a high-end level that every blade is tailored for the specific application to give maximum performance. This, and the fact that blade profiles are a trade secret of the manufacturers, this prevents standardization of modern blade profiles.
A gap exists between the blade tips and the casing, which varies in size due to the different rates of expansion and contraction. To keep the flow out from leaking around the edges of the turbine blades because of the higher pressure gradient, the blade is shrouded at the tip. The shrouded blades form a band around the perimeter of the turbine that serves to cut down gas leakage around the tips of the turbine blades, and thus improve the airflow characteristic and increase the efficiency of the turbine. The shroud also serves to reduce blade vibrations. In some cases, the airfoil of the turbine blades contain holes called film cooling holes for increased thermal efficiency. Let's now move on to blade profile selection. Originally, airfoil sections were laid out manually using a set of circular arcs and straight lines according to various empirical rules based on experience of successful designs. Turbine airfoil sections are thicker than those of compressors to withstand the very high temperatures and allow for cooling holes. Special series are used for turbine airfoils like NACA 4412 and 4415. Gas turbine airfoil sections were originally derived from the steam turbine airfoils with some modifications. These include increasing the maximum thickness and radius of the trailing edge.
For the blade parameters, the airfoil is described by a set of 11 parameters. These parameters includes the following: airfoil radius, axial chord and tangential chords, unguided turning, inlet blade angles, exit blade angles, leading and trailing edge radii, inlet wedge angle, and of course, the number of blades and throats.
High-pressure turbine. In a turbine driving an external load, part of the expansion frequently takes place in a high-pressure turbine that drives only the compressor, while the remaining expansion takes place in a separate, free turbine connected to the load. High-performance aircraft engines usually employ multiple spools. Low-pressure turbine. It is uniquely designed to provide high aerodynamic efficiency in low-pressure ratio operation to recover exhaust energy whilst minimizing back pressure.
Now, before going on to any design regarding the blade of the turbine, we must first consider the effects of different blade designs across airflow angles, pressure losses, and energy transfers across blade rows, in which one should resort to cascade wind tunnels and the cascade theory. Now, before we proceed, let us first define what is cascade and how it applies to the turbo machinery, specifically the turbine blade design. Now, by the word cascade, it means it is a row of identical blades that are equally spaced and parallel to each other, at the same time aligned with the flow direction. Taking into example the figure right here. So looking into the zoom portion of the figure, this is the cascade of the turbine blades, which are parallel and equally spaced with each other.
Moving on to the cascade measurements, there are some experimentations to be made to ensure that the blade row satisfies its objectives. And these objectives are, first, to turn air through the required angles beta 1 minus beta 2 in terms of the rotor, and alpha 2 minus alpha 3 when it comes to the stator, with the angle beta 1 minus beta 2 as great as possible to maximize the stage pressure ratio. The second objective is to achieve the diffusing process with optimum efficiency with minimum loss of stagnation pressure. As shown from the figure from the slide as an example, these experiments are generally performed on a straight wind tunnel rather than an annular form of a tunnel. Now, the height and length of cascade in a cascade wind tunnel are made as large as the available air supply allows eliminating the interference effects due to the tunnel walls. Boundary layer suction on the walls is frequently applied to prevent contraction of airstream. The cascade is then mounted on a turntable so that its angular direction with respect to the inflow duct or alpha 1 can be set to any desired value, and thus the incidence angle may be varied.
The vertical transverses over the two planes, usually at a distance of one blade chord upstream and downstream of the cascade, are provided with pitot tubes and iometers to measure the pressure and airflow angles. Pressure and velocity measurements are made by the usual L-shaped pitot static tubes. The air direction is found by either claw or cylindrical iometers. The following figures consist of the various important geometrical issues and angles relevant to the design, which are to be considered before proceeding further to cascade testing and blade design. The turbine is composed of a few stages. Each has two successive stators called nacelles or nacelle guide vanes, and rotor blade rows of small airfoil-shaped blades. The stators keep the flow from spiraling around the axis by bringing the flow back parallel to the axis. Depending on the engine type, there may be multiple turbine stages present in the engine. Turbofan and turboprop engines usually employ a separate turbine and shaft to power the fan and gearbox, respectively, and are termed two-spool engines. Three-spool configuration exists for some high-performance engines, where an engine turbine and shaft power separate parts of the compressor. Nearly 3/4 of the engine extracted by the turbine is used to drive the connected module, which is fan and compressor.
Now, when the energy is extracted from the flow, pressure drops across the turbine. The pressure gradient helps keeps the flow attached to the turbine blades. Therefore, turbines, unlike compressors, are easier to design. The pressure drop across a single turbine stage can be much greater than the pressure increase across a corresponding compressor stage, without the danger of separating the flow. A single turbine stage can be used to drive multiple compressor stage. Therefore, higher efficiencies can be achieved in a turbine stage. And that concludes our topic today. Thank you for listening, and God bless us all.